So what we were here where we found that if I now take into account the fact that the reaction zone in this flame thickness is only a fraction of the entire flame thickness, and that is where the reactions are happening, and therefore the heat release rate is going to actually come from a volume that is corresponding to only this, and I scale the reaction zone thickness over the flame thickness by a factor given by beta, which is a Zeldovich scaling factor, then I can actually estimate a u naught which has a 1 over beta term inside the square root, and so we now notice that the flame speed is about that much smaller, right, because we are now factoring in that reactions are happening in only part of the flame and not in the entire flame. We could now do further corrections in noting some more things. The question is, first of all, what we had done was to assume that W is a constant across this region, and now what we have said is W is actually a constant across this region approximately. Now that is not very difficult to imagine, because it is kind of rising very steeply within this region and going to a value, peak value, and then dropping steeply back in this region. So it is okay, but the question is, what is the W? So if you now think about what the W is the chemical reaction rate, and strictly speaking the way we have to look at, so for example in a single step reaction we should be able to write W as, I mean I am just not going to say equal to, but just going to say goes as, because I am going to write this is W in terms of mass, right. So this is actually mass produced per unit time per unit volume, and I am going to write this as something like AE to the minus E over RUT, let us say YF and YO. Maybe you can have YF power something and YO power something. As far as this particular argument is concerned, I am just assuming those powers to be 1. It is not very important what those powers are at this moment, or you can keep a power, you can say YF power NF, YO power NO, that is also fine. We can go ahead with this, but not very important for the kind of order of magnitude analysis that we are doing here at this stage. So let us say that we have this, right. The question is, this W is actually a function of T, YF and YO, right, and the T varies like this, but in the reaction zone the T variation is actually very small. It is going from a value that is very close to TF to a value TF, and looking at the way the variation happens, it is actually very weak variation within the reaction zone. So it is reasonable to assume that this T can be plugged in as TF, alright, but what would be the values of YF and YO that we have to use? As I first could estimate, what we would immediately think about is, these are actually the mass fractions of the reactants, okay. So this F is the fuel oxidized, O is oxidizer, and therefore these are the mass flow rates, mass fractions of the reactants in the incoming stream, and therefore we should actually, if you have a premixed mixture, you have a certain mixture ratio in which they are mixed, right. So there should be a certain mass fraction for the YF and certain mass fraction for the YO, and that is what we need to use, right. So that would be given by some value somewhere here. Let us suppose that this is YF and YO, which are far upstream ahead of the flame, and for us the flame is starting here with the preheat zone, right, and what we are talking about is to actually estimate a W that is going to be evaluated here. We find that the W is actually lying dormant at nearly very low values up until here because of the temperature sensitivity to E, right, but that is not because YF and YO are 0, that happens only here. You are going to have either YF or YO or both going to 0 over here. So what does that mean for our YF and YO? How are they going to vary? Can I just plug this up to this value and then now say, well, it's supposed to go to 0? Well, I think since I said TF is not going to vary a whole lot, I shouldn't expect YF to vary a whole lot and then it suddenly goes to 0. Is that the way it's going to behave? If this is the way it's going to behave, then I would rather take the far upstream value, like with subscript knots. So if in the Rankine Hugoniot formulation we had subscript zeros or knots for the upstream conditions and infinity for the downstream conditions. TF corresponds to an infinity condition, and if I were to plug in YF as YF naught and YO as YO naught, then this would actually mean that W naught infinity then goes as e to the minus E over RU TF YF naught and YO naught. Right. Now this is actually a gross overestimate of what the W is. So previously we said whatever is the W, it's constant across the entire thing, that was a gross overestimate. Then we said you now constrain this to a smaller region and got this factor, and now we find how do you actually find out the W. And if you now use the flame temperature in the Arrhenius expression and the far upstream reactant concentrations for the law of mass action, then that is an overestimate as well, because we can't expect the mass fractions to drop so steeply in this region. What happens then? How would the mass fractions change? Mass fractions of the reactants vary across the flame. That is essentially the question that we have to worry about. Okay. So the question that we have to ask is, okay, so we had reactants come in, getting heated, they get heated up and then they react to do what? So what happens when the reactions happen? They produce products, right? So the products are supposed to go that way, right? So this is the direction in which we are having the flow. So the products are supposed to go that way, but would they just do that? Would they just do that? That's really the question, right? So if you now say that you have a product concentration that sort of is the opposite of what we anticipate without thinking about a particular thing that I am coming to, then I would expect the product concentrations to probably rise like this, right, and then go all the way up to a maximum value, let us say YP infinity, alright. But if that were the case, then you can see that, oh well, the products are supposed to get formed and then flow out, but they now sense that you have a huge concentration gradient of the products over here. So what happens when you have a concentration gradient? You will have diffusion. Anytime you have a concentration gradient, you are expecting to have a diffusion, and the diffusion flux is in the direction of a region of higher concentration to a region of lower concentration. So as the products are actually getting formed, you have the fresh reactants coming and pushing them towards the other side, but as they are getting formed, they are looking around and finding, hey, I am not there, so let me try to go there. It is only that the reactant flow is trying to push them here, but they have a tendency to mix up there, right. So you now have a competition between convection of the flow of the mixture on the whole, and typically you are always thinking about convection for a mixture, okay, and upstream diffusion of the products. So sure enough, in this place where you do not have reactants happening, you had a lot of products that were produced here, you now are witnessing a incursion of products because of an upstream diffusion against the convection, and there must be a balance between these two, which is exactly the same as what we talked about for the energy balance, which is a convective diffusive balance for the product species mass, right. So effectively we should now begin to expect a product concentration profile that is similar to the temperature profile itself, because the way it happened was you now had a lot of temperature here that was produced, quote unquote temperature being produced, that is essentially heat is being produced, so the temperature is locally getting raised and then it gets conducted. That is not very different from species mass getting produced and getting diffused upstream, right. Even in the case of energy balance, you had an enthalpy flux that was trying to wash this hot region away from here, and this heat conduction was like a convective diffusive balance. It is trying to conduct heat upstream despite the flow wanting to go downstream, right. Exactly the same thing is happening for product mass, right. So this convective diffusive balance is happening for the product species mass as well, and if you were to actually now invoke a unity Lewis number for the products, right. So the Lewis number is the one that is actually trying to tell you how well a species can diffuse versus how well it can conduct heat, right. So if you had a unity Lewis number for the products, then what it means is it is going to go through the same extent of convective diffusive balance in the preheat zone for its species mass balance as the mixture went through for the energy balance. Therefore we should expect that the product concentration will be having pretty much the same profile as the temperature profile for a unity Lewis number assumption on the products, okay. So the further correction that we have to make is to take into account upstream product diffusion. Upstream product diffusion, and with unity Lewis number for the products, the product mass fraction profile can be expected to coincide with the temperature profile. What is meant by coincide? How can you actually have mass fraction that is going from 0 to 1 coincide with the temperature profile that is going from, let us say, something like 300 Kelvin to about 2500 Kelvin? The answer is, of course, we normalize, okay. So you take the maximum and the minimum and then try to fit them from 0 to 1, okay. For both cases, then you should actually expect that the profiles will coincide. Well, if that means you had a product upstream diffusion, what is that saying as far as the reactant concentrations is concerned? Concentration really means concentration, how much of what you have is there in relationship with what else is there, right. Mass fractions are all about the density of this species divided by the density of the mixture, right. So that means if you now have products over here, you have other things that are coming in and contaminating your reactants, so the reactant concentrations are going to dip, right. So effectively then you do not have either this profile for the products that you would anticipate naively without taking into account upstream product diffusion, and correspondingly we have now to alter what the anticipated reactant concentrations are going to be. So what you could expect is the reactant concentrations should now be the inverse of the product concentrations. So if you now start with something like a normalized value with respect to the initial concentrations as here, then you should expect your reactant concentrations should go like this. Now this is obviously for the deficient reaction. Let us suppose that we are considering a fuel lean situation, okay. If you now consider a fuel lean situation, then that species concentration mass fraction is going to go all the way to 0, and that is the reason why your W is also going to 0 at the end of the reaction zone, right. So now look at what happens to the species mass fraction variation within the reaction zone. Instead of actually having a value that is about that high, you are now looking at a value that is about so small, okay. There is hardly any variation of this away from 0, so we are now talking about fairly small values. So correspondingly you should anticipate that if your W were to be calculated with GSTF, which is alright, you should probably actually now have a factor beta thrown in on your YF, okay. We have to now decrease the amount of YF relative to the initial or the far upstream value, and therefore we have to bring that in, right. So in fact we could just for the sake of completeness go back and then say, let us suppose that this is M and N and we want to say M and N. So correspondingly the reactant concentrations will decrease with the deficient reactant going to very low values in mass fraction in the reaction zone, right. Now if you think about, so that means we should basically say that is YF for example should now actually be more like YF divided by beta. So correspondingly our W should be going as what we would call as W naught infinity divided by beta power m, right. So you would now say YF is YF naught divided by beta, so beta power m should show up for your denominator with W naught infinity in the numerator to give you a W. So question then is what happens to the excess species, okay. So the excess species could actually come out like that to whatever value, let us say YO infinity, alright. Now that is an appreciable fraction of the original value, and so if you, from an order of magnitude basis, it's probably a factor of about 2 or 3, that's not a factor of 10, so it's not really an order of magnitude different, right. So without worrying about the non-deficient or excess species mass concentration reduction, we are still within an order of magnitude, okay, within the order of magnitude in our estimate, so that's reasonable, so you don't have to worry about this, that's essentially how we should want to look at it. On the other hand, if you're thinking about like a stoichiometric mixture, then both of them are going to be equally deficient, right, so you have to make this correction, so keep that in mind. So that's an additional correction that we want to do. We want to go back and say this W is not going to be just W naught infinity, right. This beta here was to make sure that this W, whatever it is, W naught infinity or not, is going to be confined to a small region when compared to the flame thickness. But on top of it, if you now say W is actually W naught infinity, then that correction basically says no, it is not, it is W naught infinity divided by beta power m, that's what that you have to plug in there. Alright, can we do more, right, can we anticipate something more than this, or are we really pushing our luck trying to get insights into how things are supposed to happen, right, without doing the mathematics. Okay, we are hardly doing much mathematics here, we are just doing mostly order of magnitude, anticipating things, how they are supposed to happen and so on, right. So in fact I specifically say expect it to coincide, that's the crux there to get you this, and this is not robust, to say that this is going to be like this is not robust, it's just an order of magnitude estimate. Good, then what else can we do? What have we made an assumption here on? We have made the assumption about unity Lewis numbers, right. We have made a unity Lewis number assumption on the product to say that it's going to coincide with the temperature profile, alright, and correspondingly if you now say that if the product concentration profile is like this, the reactant concentration profile should follow like this is how we have actually built up our argument. Now that implicitly then assumes that the reactant Lewis number is also 1, right, because effectively whatever we talked about for the product happens for the reactant species mass balance as well. That means as far as the reactant species mass is concerned, you have a convective diffusive balance in this region for the reactant species mass, right, and if you now assume that the length scale of this particular balance is the same as the temperature profile, then we are implicitly assuming that the Lewis number for the reactant species is also equal to 1, right. That means the species, the reactant species can diffuse just as well as it can conduct heat, is what we are basically assuming. That need not be the case, and that is why are we talking specifically about the reactant Lewis number and just forgetting about or abandoning the product Lewis number that we originally constructed our argument based on, is because the reactant concentrations, the ones that are showing up in the law of mass action, that's what we are beginning to correct, and we want to now see if a reactant Lewis number is not going to be 1, is it going to be this way or that way, right, is this profile going to actually change, right. So how do you take this into account? There is a quick way of doing this. So for the correction, consider non-unity Lewis number of deficient reactant, right. So how do you expect the reactants profile to behave, and how do you expect the temperature to behave? So in the convective diffusive zone, which is the preheat zone, right, we could apply the Schwab-Zeldovich formulation. And what would you have? Let us suppose that you had a velocity u naught which didn't change significantly, then you have a convection balanced by the species diffusion. You can write, right, it's assuming a fixed law formula, fixed law kind of diffusion going on, and a u naught dt over dx equals alpha d square t over dx squared. Now what you are going to do is just focus only on this particular region, and as far as this region is concerned, you are going to simply say, let me not worry about the difference between this and this, okay, let me not worry about the difference between this and 0, right. So it's as if like it started from this value and went to 0 here, you started from this value and went to TF there within this region, okay. And so with these kinds of boundary conditions that you want to apply, in fact you should be able to also fix your coordinate system and say that these values are actually at negative infinity. So if you now apply these kinds of boundary conditions, you can get solutions. I am not rigorously solving this step by step for you, just going to write the solution here and trying to explain the adoption of these boundary conditions intuitively. It's not very important for us to go through the steps at this stage. Well, let us go back and write dF to be taking into account the diffusivity should be of the fuel particularly, which is not necessarily the same as the other diffusivities of species, and here you are going to have T equals T naught plus Tf minus T naught times e to the u naught x divided by alpha. So let us see what is going on. It is easier to see this first. This is what we have been considering first, the thermal profile. You see what is going on. We have a temperature that is now going to actually increase in excess of T naught by a difference of Tf minus T naught times a exponential factor, right, which obviously is going to actually increase exponentially beyond the preheat zone. So the temperature, as far as this profile is concerned, is going to give you something that keeps going like that, okay. Disregard that, that is not part of our domain as far as this equation is concerned. This equation is valid only in this domain, okay. So once you understand that, then this profile is quite reasonable for you to think about, right, and correspondingly you will now have your Yf starting from Yf naught and decreasing by this factor, okay. Why are we doing this? We want to be able to see this in both the cases, right. So as x increases within the preheat zone, you are now actually looking at an exponential of x divided by df divided by u naught, right. So the length scale for reactant diffusion is, or should say characteristic length scale, right. Characteristic length scale for species diffusion is df over u naught. Are we okay? This is like meters squared per second, this is meters per second. So meters squared per second divided by meter per second should give you meters, right. So always have to, whenever you come across these kinds of things, you have to quickly check your dimensions, right. Then the characteristic length scale for heat balance, right. This is in the preheat zone for the convective diffusive balance, right, is alpha over u naught. That is a characteristic length scale. So the ratio of the characteristic of the length scales of fuel concentration to temperature profiles is then df over u naught divided by alpha over u naught, which is equal to 1 over LEF, because LEF is alpha over df, okay. So what do we have? If your Lewis number of the fuel is greater than 1, alright, then the fuel concentration length scale is going to be less than the temperature profile length scale. That means if I go back and use a different color chalk piece and say forget about that, that's a X species. So what you are talking about is we are saying that this length scale for the species is now going to be delta F LEF greater than 1. If I had a Lewis number for the fuel greater than 1, then 1 over something greater than 1 is less than 1, therefore df over u naught is less than alpha over u naught, and therefore this distance should actually be less than that distance. So instead of just talking about a single delta, we will now talk about a thermal flame thickness, and then we will now talk about a mass flame thickness, right. So what then happens is, how do you now think about the concentration profiles? The concentration profile is now going to actually begin to drop only here, not here, right. And considering that it is continuing to be a deficient reactant, let us say for the fuel is what you are talking about, you have to get back to this as you come down. So you are now going to drop a line that goes like this. Well, let us try to make this a little bit better. So what has happened here? What we find is, instead of having a variation that was like only so small within this region, right, you are now having a larger variation within the thermal region, right. So that means your concentrations have to be taken to be higher than what we did here. So this beta was to take into account the reaction zone based on the thermal flame thickness, right, scaling the thermal flame thickness for the reaction zone thickness. But we find that as the Lewis number is greater than 1, the concentrations in the reaction zone based on the thermal flame thickness will be higher than this. So correspondingly we have to say right, YF then will become YF0 divided by beta times LEF, because LEF is greater than 1 and we need to now multiply by this excess LEF then unity to factor in that your concentration is going to be more. Now of course we hope that this factor of multiplying LEF should now be the same when you now think about a LEF that is less than 1, right. So how would that work? So maybe take a different color chalk piece, let's try pink. When you now say that LEF is less than 1, then the species mass balance length scale is going to be greater than the thermal balance length scale, right. So that means we should now be thinking about a flame thickness based on this to be delta F LEF less than 1. And how would you draw your profiles? You would start from here, but you would start dropping your concentration right here and then reach up to this point, right. So that would be something like this. What you then find is the concentrations are even lower than the situation corresponding to a unity Lewis number. So the Lewis number was actually less than 1 for you, so you just multiply by that factor to get a concentration that is less than that. So sure enough, so you need to have this kind of a multiplication going on. Therefore then your W should go as W0 infinity times LEF divided by beta power m, right. So this is what we could actually plug in back here to now not only take into account upstream diffusion of products and correspondingly downstream diffusion of reactants in addition to downstream convection of the reactants, so that the concentrations of the reactants are actually coming down in the reaction zone. We could also now look for preferential diffusion. That means you now say when you have a non-unity Lewis number, the reactants actually diffuse preferentially depending upon their Lewis number relative to the thermal balance, right. And then we find that the concentrations of the deficient reactant, which is more critical in the reaction zone, can vary with the Lewis number itself in a way that we can see. So this is amazing in my opinion, because we just think about what's going on, okay, and then start expecting how these variations should be. And the interesting thing is, if you have to do the rigorous analysis, as we will momentarily commence to do, number one, we will be constrained to make assumptions particularly about unity Lewis number. Like for example, the Schwab-Zeldovich formulation essentially assumes one of the assumptions is the unity Lewis number. So if you now adopt the Schwab-Zeldovich formulation to solve the problem of a one-dimensional laminar flame, premixed flame propagation, then we will be constrained to do this for a unity Lewis number. And then we will have to relax the assumption of unity Lewis number and then expand the scope of the analysis and then take the burden of non-unity Lewis number upon ourselves and do a fresh analysis for that. What you will find at every stage of doing the mathematically rigorous analysis with a unity Lewis number assumption, that is up to this stage, right, or taking into account a non-unity Lewis number and reaching up to this stage, you will find that the mathematical analysis is different from this only by a factor of square root of 2, right. Otherwise you get all the factors that you want in there in the way we have done this. Square root of 2 is like 1.414, so your order of magnitude estimate is actually okay within about 41%, right. That is essentially the power of the order of magnitude analysis. the additional bonus is we started actually using some of our gray cells instead of just plugging and chugging equations and so on, which we will now do.